another minute or two. Only 3 people here besides myself. Wait another minute. Let's try to get at least one more person before we start this. All right, it's 10:02. Let's get started. First of all, I wouldn't want to end the semester without recommending one more book. There is a freely available online book that's kind of a classic of the field called Space-Time Physics by Taylor and Wheeler. And it's all about special and general relativity. You could download a PDF right now if you wanted. And learn more than I'm going to be talking about regarding curved space-time. With that said, what we're going to discuss today is just a little bit of general relativity, just a little bit about relativity and gravity. We are right on the edge of what I know. We are in dangerous turf, and so you should take my discussion here not as the final authoritative word on anything, but as an illustration of how one might try to analyze things that one is still working through. So general relativity is founded on something called the Equivalence Principle. There's a few ways of phrasing it. The one we're going to really work with today is that all inertial frames are equivalent, all of them. And we're going to push hard on that. That's not the way it's usually stated. It's usually stated in one of two ways. It may be stated that all objects fall at the same rate in a gravitational field. That is an experimental finding. That is not some first principle. It's not something we could conjure from pure thought. It's something that is simply known from experiment. If somebody were to ever find an exception to that, then we would have to deal with it. We would have to take it seriously. But related to that is the idea that a gravitational field is equivalent to being in an accelerating reference frame. let's say we were in outer space. We were on a rocket ship, all right? And the rocket is accelerating. Well, the ground beneath our feet, the floor beneath our feet would be accelerating towards us. It would be pressing against us, which means we would be pressing against the floor. And if we were to not look outside the window, if we were to just be in this windowless room, we would feel like the floor is pressing up on us, and depending if they ran the rocket engines at the right rate, we might feel the floor pressing up on us at 9.8 meters per second squared. We could not do any experiment inside that room that would tell us whether we are on Earth or on a rocket ship. Now you may be thinking, well, come on, that's ridiculous. Of course there's a difference. Yeah, there is. And if we opened up the windows, if we dismantled some of the floor panels and looked below us and saw thrusters, then yes, we could tell that we are on a rocket ship. If we, started looking for the magnetic field of the Earth, although even then you could ask, what if there's magnetic shielding? The point is that if we were to look at the world around us beyond our immediate confines, we could, of course, figure out, all right, are we being pressed against the floor because of a thruster below the floor, or are we being pressed against the floor because there is a giant rock with radius 6.4 million kilometers? 6.4 thousand kilometers, 6.4 million meters. Then we could tell. But just by local experiments, just by gathering data in our most immediate vicinity, we could not tell. And if we can't tell with any experiment, then that means that the laws of physics have to be the same in an accelerating reference frame or in the vicinity of a giant rock exerting a gravitational force. Likewise, if we are in a room built on a hillside and the floor beneath our feet is uneven, well, then, gravity is not going to be pointing into the floor, it's going to be pointing at an angle. Likewise, if we are on a train car that's accelerating, if we let go of something, it will not fall straight down to the floor. Depending on the direction of the acceleration, it will accelerate at one angle, one diagonal, or the other diagonal, all right? And again, we could tell, are we in an accelerating train car by looking out the window or peeling away the floor and seeing that there are wheels beneath us. We could tell if we're on a hillside by looking out the window. But if we don't do that, if the only thing we do is experiments where we just let go of things and watch them move only in our most immediate vicinity, then with these local measurements, we cannot tell. And Einstein thought deeply about that, and from that, he constructed the theory of general relativity. But for now, let's stick to inertial frames. A really easy inertial frame would be a spaceship halfway between here and the Andromeda Galaxy. There's absolutely no gravitational field of any significant strength, so we let go of something and it just sits there right next to us. If that isn't an inertial frame, nothing is. And somebody might start talking about gravitational effects, general relativistic effects on time scales of billions of years. Sure, but that would again be a non-local experiment. That would be an experiment that takes place over an extended region, not of space, but of space-time. There's a less intuitive inertial frame, and Einstein thought of this less intuitive inertial frame 2 years after publishing his special theory of relativity while he was still working at the patent office. And he described it as the most wonderful thought of his entire life. Let's say we've got an elevator falling down an evacuated shaft. Evacuated is important so that there's no air drag. This thing is falling at 9.8 meters per second squared under the influence of the giant rock below it. All right, and there's no cable on it, so there's nothing to exert a force except for the earth. So the elevator's falling. You're falling. You let go of an object in your hand, and it's falling. Well, all of you are falling at the same rate, or let me rephrase that. An observer standing, looking at you, standing on the ground, looking at you, looking through the window of the elevator, if there is such a thing, that observer says, you're falling. But let's say that there are no windows, and let's say that we're doing local measurements. And here I mean local in space and in time. If you wait a few seconds, you're going to crash to the ground. And in that fraction of a second before you lose consciousness from the collision, you're going to say, oh, I was falling. But that's non-local, meaning that you had to compare measurements now and later. That was at two different instants in time, all right? You may be thinking, well, it's local in space. Sure, but it's not local in time, so it's not local in space-time. So if you just let go of something and watch it for an instant, it doesn't accelerate. It doesn't move away from you. You're in an inertial frame. It's in an inertial reference frame. And as far as the laws of physics are concerned, that will continue to be true until something like, say, the floor of the basement of the building that the elevator will eventually reach intervenes. But if we ignore practicalities, remember, we're physics majors, we chose not to major in engineering. If we ignore practicalities, then as long as that thing's falling, you're in an inertial reference frame. And I know I'm harping on the obvious, but it's something that screams out not an inertial frame, because you just visualize the experiment from the outside world. You say, come on, it's falling. Come on, there's acceleration. Come on, it's going to stop falling pretty soon when it hits the ground. But remember, locally, for that time, while that's going on, the laws of physics for that person in that elevator car have to be the same as in any other inertial reference frame. Any questions? Okay. Here is seemingly the most obvious fact in the world. We're in an inertial reference frame. We turn on a laser. That beam of light goes in a straight line at constant speed from one side of the elevator to the other. And if we put a little bit of fog in the elevator so we can actually visualize the laser beam, we would see a straight line. It's the only thing we could see. End of story, right? Well, let's go away from the elevator's reference frame. Let's go away from that inertial reference frame to the reference frame of someone on the ground. And you're thinking, well, that's someone on the ground. They're in an inertial reference frame. And I say, no, they're not in an inertial reference frame because they let go of something and it falls away from them. And they're watching this elevator fall. And so let's look at the elevator at 4 different instants in time. Here's where the light is. You got a little laser on the side of the wall. Here's where the light is initially. Hasn't just barely left the laser. A little red glow on the lens. The light starts traveling. The elevator has fallen this distance. The light has gotten this far. It is now over here. And you may be saying, but wait, in the reference frame of this person, the person on the ground, it was just going to the right. Well, the person on the elevator says that the light went to the right and that sometime later the light was to the right of the laser. And we might disagree on a lot of things, but we should be able to figure out whether some fog over here scattered light or not. I mean, when the laser light hit that fog, it made the fog light up, right? It probably heated it up a little bit. There are objective, tangible, material facts of reality that we have to be able to agree on. A little while later, the elevator has continued falling, and if in the first instant it fell a distance delta y, if I double the time, the distance fallen in a time interval is proportional to the square of the time interval. This is just freshman physics. Y equals -1/2 gt squared. So if I double t or delta t, I have to multiply y by 4. It's fallen farther. So now the laser fell 4 times as far. Before it fell half a grid square. Now it's fallen 4 halves or 2 grid squares. So the laser has fallen here. The light must now be here. We go 3 time intervals. The light has now traveled all the way to the other wall. Right now, some water droplets in the fog in the elevator are scattering light over here. A water droplet is heating up over here. We better be able to agree on that. Either a water droplet did or did not vaporize when it absorbed some energy. It's now fallen 9 times as far because, again, the distance is proportional to t squared. Multiply t by 3, we multiply t squared by 9. So if we put all those facts together, you see how each time the light has gone farther and farther from this line. The light followed a curved path in space. And that must be the case, because if we agree on inertial reference frames, if we agree that in inertial reference frames, the laws of physics are, well, simple is a strong word, but as simple as they had been for the last 15 weeks, then whatever happens with this person in this reference frame must be valid. And whatever we see in other reference frames, there must be a way, they might not be the same thing, but there must be a way to reconcile those experimental facts. We've got to be able to agree that there was a water droplet that was immediately to the right of the laser, and that water droplet heated up. We have to be able to agree on that, because that's a tangible material fact of reality. And if material facts of reality are different in different reference frames, then we aren't in physics. We're in Westworld, where the robots have their memories altered and everyone sees things differently. Questions so far? So to the people on the ground, the people looking through the window of the elevator, they are in a non-inertial reference frame because they let go of something that falls. That's the result of gravity. They see the light taking a curved path. And this is a prediction of relativity, and this prediction of relativity was verified in 1919. In 1919, there was an eclipse. And so somebody looked at a star that should have been right near the sun. But because the light going from that star passes right near the sun, its path gets bent. And so when it travels to Earth, it travels as though it came on a different path. It's following a curved path in the gravitational field of the sun. It comes to Earth at this angle when its path gets bent. It looks like it comes from over there. And they had to do that during an eclipse because there's no way you could see a star that's right next to the sun in your field of view, or almost next to the sun in your field of view during the day. They had to wait for the eclipse so that all of the light from the sun and all of the light from the sun that gets scattered in the atmosphere was blocked out. Now, this is claimed as, or at least it was claimed as, a vindication of the theory of relativity. But there are countless controversies. Historians of science who have reviewed the original lab notebooks have spent decades arguing over whether or not Eddington, the astronomer who did these observations, did them accurately. Did he fudge the data? Did he misinterpret? If he misinterpreted, did he misinterpret deliberately? Did he misinterpret on accident or out of wishful thinking? I'm not qualified to judge that. Here's what I can say. I can say that however good or bad those experiments were, they weren't as good as we would like. Subsequent experiments have completely borne it out. That doesn't necessarily vindicate Eddington. If Eddington did his measurements wrong, then he did them wrong, and we should critique that. But the theory has been vindicated. That I can say. The other thing I can say is that it is fascinating to see what happens when people look behind the curtain and see how the sausage was made, to mix some metaphors. Now, that was actually called the, by the way, any questions about that? I just told you the light doesn't travel in straight lines after spending the whole semester telling you that waves do that rays of light travel in straight lines. Waves might spread, but even then you can take the wave and break it down into plane waves that travel with well-defined directions. And now what I'm saying is that once we bring gravity into the picture, even the thing that we call a plane wave doesn't have a single well-defined direction. It has a changing direction. That was called the second classical test of relativity. And it was called the second classical test of general relativity because there was a prior test. It's a test that I can't really give you a quantitative explanation for because it would require going much deeper into general relativity than we have time for, or frankly, I have training for. But I can give you, I could almost do it, but I would still need 2 more classes to do it. And with a little bit of prep, I could definitely do it. But again, we would need 2 more classes because there's a lot of material to get there. But in short, the first test of relativity, of general relativity, was the precession of Mercury. We know from Kepler and Newton that if your force is inversely proportional to the square of the distance, then you should get elliptical motion of planets. So let's consider Mercury. Well, Newton and Kepler would predict that Mercury goes in an elliptical trajectory. Except in fact that ellipse precesses, meaning that on each trip, it follows a slightly different ellipse. The ellipse gets distorted from what it originally was. The ellipse rotates through a small angle on each trip. And the effect is very tiny. And most of it can actually be explained by Jupiter, because Jupiter is also exerting a force on Mercury. It's exerting a force on all of the planets, and all of the other planets are exerting forces on Mercury and each other. But Jupiter is the dominant effect because Jupiter is more massive than any other planet. So Jupiter exerts this huge force. And remember, this prediction of elliptical orbits is assuming that the only force acting on the planet is the force from the sun. As soon as you add other forces, the orbits become more complicated. In principle, though, in practice, though, those complications are very tiny. So every planet's orbit is almost elliptical. And then Jupiter and other effects just perturb it slightly. Well, over the centuries, people had gathered good data and they'd watched the orbit of Mercury. And they had done calculations to account for the effects of Jupiter. And the effects of Jupiter explained most of it. But there was still just a little bit of discrepancy that they couldn't quite account for. And their measurements had gotten quite good. And we're talking substantially less than a degree per century. Not a lot. The problem is that even though it's minuscule, they had done really good measurements. And they had calculated the effects of Jupiter. And they had calculated those effects really, really well, even before they had computers like we have today. And they still couldn't explain this tiny precession. And no one had any clue what was causing it. But Einstein's thought process was, well, okay, I'm coming up with a theory of gravity, and I'm predicting that gravity will behave slightly differently than Newton predicted, and that those deviations from Newtonian behavior will be most noticeable in strong gravitational fields. Well, of all the planets, the one that feels the strongest pull from the sun is Mercury because it's closest. So if there's anything in our solar system that might exhibit deviations from Newtonian behavior, and not deviations that could be explained by Jupiter, because again, if they can be explained by Jupiter and Jupiter's gravitational field is, well, stronger than any other planets, but still weaker than the sun's, it's weak enough that it's Newtonian gravity. So that would be a Newtonian effect still, a weak yet complicated Newtonian effect. Weak in that the field isn't strong, complicated in that it gives rise to elaborate orbits. But Einstein said, if relativity can explain some discrepancies with gravity, then the one place where it's going to be most noticeable is Mercury. And so he constructed his theory of gravity, derived his equations, and then he used those equations to predict how these additional gravitational effects would change the orbit of Mercury. And lo and behold, they changed the orbit of Mercury by almost exactly the same amount as people had observed, to well within experimental error or observational error. And it's actually, it's hard to derive this. To actually derive it requires a whole bunch of calculations. It requires introducing new concepts and taking about a week of derivation. But once you do it, the result is that the force, the acceleration produced by gravity is mass times Newton's gravitational constant, big G, There's still a 1 over r squared. And then there's another constant over r to the fourth. You may be thinking, well, I see alpha over r to the second. Think of this as mg over r squared out here, multiplied by 1 plus alpha over r squared. So the 1 just gives you the Newtonian force. The alpha gives you all the discrepancies. And alpha over r squared times mg over r squared is alpha mg over r to the fourth. So we've got a term that has 1 over r to the fourth in it. It's part of the gravitational acceleration. And you can write a simple Python program using techniques that you'll learn this fall in computational physics if you take Dr. Binder's class. And when you run those calculations and you watch the orbit of Mercury, here I've set up a planetary orbit with initial conditions that match Mercury's orbit, so distance from the sun and velocity matching Mercury. I made alpha large. I have to make alpha large because if I don't make alpha large, you won't see anything. But we can exaggerate it. Instead of getting an ellipse, this is several orbits, you may be thinking, well, I see an ellipse with weird thick lines. No, what you actually see is several orbits. Those orbits don't quite fall on top of each other. And so the effect, once you go through the concepts of general relativity and derive that additional 1 over r to the fourth term in the force or acceleration, then calculating the effects of that term, you could do with a simple Python program as a homework assignment in computational physics. And Einstein did that without a Python program because he's Einstein. And he immediately got the right result and he put that into his paper. That's actually a lot of how theoretical physics works. You come up with a theory that encapsulates some ideas that you think are needed in order to fit things together. And then you try to extract a prediction from that theory, and that prediction had better match at least some known data. And then you propose additional experiments. And one of the additional experiments that he proposed was the deflection of light. But the first one was the precession of Mercury. Any questions? Okay, here's the third classical test of relativity. Clocks run at different rates at different points in a gravitational field, or photons get Doppler shifted in gravitational fields. Let's go back to our falling elevator. Start out, I look through the window, I see someone's clock. A little later, I look through the window, I see someone else's clock. A little later, I see another clock. Now, each of these clocks is moving past me more rapidly than the previous one, which means that each of these clocks is running at a different rate. And if we think back to the twins paradox, the twin on the spaceship was not in an inertial reference frame, and they aged less than the twin on Earth, who was in, well, we'll call it an inertial reference frame. It was a more inertial reference frame than the twin on the spaceship. So if somebody's moving rapidly relative to you, they age less. Their clock must be running slower, all right? And so the discrepancy, omega, one of the frequencies is the other one divided by square root of 1 minus v squared. So this discrepancy is omega naught times the change in 1 over square root of 1 minus v squared. Well, let's see here. 1 over square root of 1 minus v squared, we can write that as mass plus kinetic energy over mc squared, because mass plus kinetic energy would be mc squared over square root of 1 minus v squared. Now, we know that we want to try to relate this to gravity. The change in mass plus kinetic energy is minus the change in gravitational potential energy. And so that is omega naught times g delta y over c squared. So the person on the elevator sees the clock running at different rates. Now, the person in the elevator sees their own clock hands. You know what? Let's just ignore that. I said that wrong yesterday when I was writing this out. Here's the key point. The clock lower in the gravitational field runs at a slower rate, whereas an inertial clock high up in the gravitational field, like on the satellite, is running faster, okay? So GPS satellite clocks are running fast relative to clocks at the ground. Now let's talk about GPS. You get signals from at least 4 satellites with 4 different delay times. You basically just ask the satellite, hey, what time is it right now? And the satellite tells you. And even if we ignored relativistic effects, you know, if you ask someone somewhere else, what time is it? They're going to give you the time when they send their signal, not the time when you receive your signal, all right? There's going to be a delay. And that delay between the two is going to tell you how long the signal took to get from the satellite to you. So now you know how far you are from the satellite. Well, there are lots of points on Earth that would be that distance from the satellite. And there would be, you ask another satellite, hey, what time is it? It's going to tell you, and of course that there's going to be a delay. And again, you know, you would get the time somewhat later, and you can figure out how far you are from that satellite. Well, there's a bunch of points on Earth that are that distance from the satellite. And you ask a third. And with those 3, you are able to narrow down your location. Now, you have to actually ask a 4th, because somebody could always say, well, what if your clock is off? You know, I can almost guarantee you that the clock on your cell phone is not as accurate as the atomic clock on a satellite. So there's some offset between your cell phone clock and the atomic clock on the satellite. And that 4th one can be used to calculate that offset, basically. All right, so I know how far I am from each of these clocks. I know the offsets. I figure out where I am. Any questions on that concept? Now remember, I said that the clock rates are different by an amount omega naught g delta y over c squared. Well, if I add up g delta y over many delta y's and take into account the fact that g is changing, you know, the gravitational field strength very far from the Earth is different from the gravitational field strength at the surface of the Earth, then I've actually got to do an integral of g dot dr, and there's a minus sign because g and dr point in opposite directions. Now, we're getting the time on that satellite, which is above us in the gravitational field, and its clock is running faster because of gravity. But there's also the fact that the satellite is moving relative to you. You know, we're here on the ground. We complete an orbit every 24 hours. That's how fast we're moving in a circle. Well, the satellites are moving faster than that. They complete an orbit every 12 hours. And so we have to take into account the relative velocities. And so we take that into account. There's a square root of 1 minus v squared in here. And that's going to create a discrepancy if you calculate, if you run the numbers through a calculator, of 1 part in 8.4 times 10 to the minus 11. Then there's a discrepancy due to gravity. By the way, this would make the clocks above us run slower because they're moving relative to us. They're going fast relative to us. So special relativity would make them run slower. General relativity makes them run faster. We have to compute the difference between those two effects. General relativity, well, delta omega over omega naught is minus 1 over c squared integral of g delta y. So we integrate minus dr over r squared. We've got the mass of the Earth times g, big G, over c squared. We plug all of this in, and we get 1 part in 5.3 times 10 to the minus 10. So we get that the clocks up there are running faster by this amount due to gravity and slower by this amount due to their relative motion. We multiply those two factors, 1 minus this factor times 1 plus that factor. And here's our discrepancy. 4.5 times 10 to the minus 10, less than half a billionth. Doesn't sound too bad, being off by less than half a billionth. But that's the rate, okay? That is the change in the rate. So in the course of a day, 24 hours, we get a backlog of the day's duration, 24 hours times 3,600 seconds per hour, roughly 100,000 seconds, multiplied by this percent error. We get a discrepancy in just one day. If we let an atomic clock run on the ground and we let an atomic clock run up in space, after a day, that discrepancy of half a billionth, well, half of a billionth of a day is 3.8 times 10 to the minus 5 seconds, 38 microseconds. Okay, 38 microseconds, that doesn't sound like much. If your only goal is to get to an appointment on time and you're 38 microseconds late, no one's going to say anything. They're going to say, you walked in just in time. But GPS is about timing radio signals that get from a satellite to you. And if we are off in the timing of a radio signal by 38 microseconds, the distance that a radio signal travels in 38 microseconds is 11.5 kilometers. GPS would be useless for that. If GPS didn't correct for relativity and you were to use GPS on the second day that it was running and you were off by 11.5 kilometers, that would be 8 miles roughly. You'd be 8 miles away. That's completely useless. Any questions? The GPS system is a daily test of the theory of relativity. Because remember, it would be off by 11.5 kilometers on the first day, 23 kilometers on the second day, 34 kilometers on the third day. And this thing's been running for more than 40 years. It was started in the 70s. By the late 70s, the first units were online. It was only being used by the military. As the military became more confident in releasing this and as consumer electronics got cheaper, it went mass market. This thing's been running for 40 years. It is a daily test of the theory of relativity. So whenever a crackpot says that Einstein was wrong, well, the fact that they say Einstein was wrong, that in of itself does not make them a crackpot. But I'll tell you this much. If Einstein was wrong, he was wrong only in certain cases. Or maybe he was wrong in this case, but he was wrong by a very, very tiny amount. He was wrong by an amount so tiny that the discrepancy still hasn't added up to anything measurable after more than 40 years of GPS. As a matter of fact, early in the 2010s, the Europeans sent up a GPS satellite, except the GPS satellite was launched incorrectly. And so it wound up in the wrong orbit, which meant that instead of being in a circular orbit, it was in an elliptical orbit. Sometimes it would be closer to the Earth, sometimes it would be far from the Earth. So the frequency of the clock on the GPS satellite that was in the wrong orbit, that frequency is wrong. It oscillates. And some scientists decide, well, we've been given a lemon, let's make lemonade. So they did calculations to figure out what the discrepancy would be in that clock when the discrepancy oscillates. And it doesn't quite oscillate evenly, so it doesn't quite average to zero. So basically, they put a satellite into a complicated orbit, took nearly a decade of data, calculated what should happen to that atomic clock, compared it with what actually happened, and the relativistic predictions match. So again, I can't tell you that every facet of relativity is correct. What I can tell you is that we test it daily, we use it daily, We use it for everything from navigating around the neighborhood to fighting wars, and it works. I can also tell you that the Air Force, when this was first launched, apparently demanded that they write 2 versions of the software, one that includes the relativistic corrections and one that doesn't. And some people laugh at this, saying, look at those generals, they don't know anything about science, they think Einstein was wrong. Well, there were certainly experiments before the late 70s indicating that Einstein was right. We'll talk about one of those experiments in a moment. But what I can tell you is that until you've done massive global scale testing for decades, how would you know it's right? How would you know it's going to be that reliable? I can also tell you, I probably told you this story already, but Albert Michelson, the guy who did the experiment that many people would say demonstrates that there is no ether, that I say many people not because I'm trying to be a crackpot, because all of this stuff is subtle. Michelson himself said that there was room for other interpretations, not a lot of room. He spent the rest of his career doing other experiments and reporting them accurately. So even though he never fully accepted relativity, no one considers him a crackpot, because the statement he made was never Einstein was wrong. The statement he made was, I cannot rule out, I can rule out these versions of an ether theory. I have not yet ruled out those versions of an ether theory. Let's do a good experiment. Anyway, Michelson started his career at the Naval Academy. He went to college at the Naval Academy. He was actually an immigrant, born in Poland, moved to Nevada, grew up in Nevada, got on a train, went to the East Coast, knocked on the door of the White House. That was when you could do that. Nowadays, you knock on the door of a booth where a guard, if you're on a list, takes you to another booth where they check your list again, and you go through several rounds of that. He knocked on the door of the White House, begged the president for an appointment to the Naval Academy, got in, graduated, served in the Navy, went back to Naval Academy as an instructor. Working as a professor there, he did experiments to measure the speed of light, and his work on the speed of light eventually led to GPS. So the Naval Academy commandant who allowed him to engage in that research should be given a posthumous Distinguished Service Medal, because he laid the foundation for GPS-guided bombs, which from a military perspective is a huge achievement. Any questions? All right, we don't have to think of this in terms of clocks. We can also think of this in terms of the frequency of an electromagnetic wave. The received frequency, we think of a clock as producing an electromagnetic wave, and the ticks of the clock are just the peaks of an oscillating field. Every time the oscillating field is at its peak, you feel a stronger force. That ticks your clock, all right? That's like the tick of a clock. That's like causing the mechanical motion. So if we say that a clock down here is running slow relative to us, well, the clock down here doesn't know it's running slow. The clock down there is running off of whatever atomic transition. It's emitting that photon. All the people down here say, hey, it works. All the people up here say, no, we're seeing that atomic transition run slow, which means that the photons emitted down here must have been shifted to lower frequencies by the time they got up there. That's just another version of the Doppler effect. So we once again have Doppler shifts of photons. Now here's a fun thought experiment. We've been talking about particle collisions and relativity. So let's say we have a particle and an antiparticle collide with each other down here. They emit 2 photons. The photons go this way and that way. They bounce off mirrors. The mirrors send them up here. They go up here. The 2 photons recombine to form a particle and antiparticle. You may be thinking, can photons do that? Yes, it's a very, 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 very rare process, but they can do that. So the photons recombine, they form 2 particles. The particles are up here. They're not down there, they're up here. So let's say they fall. They gain some kinetic energy. Once they're down here, they collide, they emit 2 photons. Those 2 photons have higher energy because These weren't two particles at rest. These were two moving particles. So the energy of the two photons created has to match the kinetic energy of the energy of the two photons created has to match the kinetic energies of the particle and antiparticle plus the masses of the particle and antiparticle. So now we've got high energy photons. They're emitted. They bounce off mirrors. They come up here. They recombine. They form some fast moving particles, which then fall. They gain even more kinetic energy. We emit even more high energy photons. And we do this over and over again. We would have a perpetual motion device. The only way this doesn't happen is if when those photons rise, they get Doppler shifted. Their frequency decreases. Because the energy of a photon, as will be discussed next semester in 2540, turns out to be Planck's constant times their frequency. So if there wasn't a gravitational frequency shift, then we could have a runaway process that violates the law of conservation of energy. Any questions? All right, last thing. The GPS didn't happen until the late 70s, but we knew about gravitational redshifts of photons by 1959. Let me rephrase that. We knew in 1915 that general relativity predicted it. We knew in 1959 that the prediction is actually valid. It was called the Pound-Rebka experiment, done at Harvard by Pound and Rebka. They have a gamma ray source down here in the basement. A few floors up, 22.5 meters above, they have a gamma ray receiver. And the source and receiver use identical transitions. Change in energy going from ground to excited when the receiver gets a gamma ray will be Planck's constant times the frequency, or h bar omega, 14 keV. That's the source they used. But if the gamma ray loses energy or reduces frequency when it gets up here, we shouldn't be able to detect a photon. That doesn't mean that the photon didn't come up here. It just means that this device will not be able to detect a photon if it gets up here because it will have too low of a frequency for this thing to absorb it. So what they did, you could either put the receiver or the source or both on a speaker, just a stereo speaker, right? Stereo speaker vibrates up and down. So if our receiver is moving towards the photon, well, there is a Doppler shift. Remember, whenever your detector is moving towards the photon, your detector sees a wave with a higher frequency. Conversely, if the source down here was moving, a moving source emits photons at a higher frequency. So you could do it either way. And if the Doppler shift due to the motion of one or both of these devices just cancels out the Doppler shift due to gravity, well then lo and behold, you are going to get absorption of a photon up here. So basically they turn on the speaker, they play with the amplitude and frequency of the speaker so that they get just the right velocity as the surface of the speaker is moving up and down. And when they get just the right velocity, you get absorption. Now it's actually a little more complicated because it's moving throughout its cycle. And at some point in the cycle of the speaker, it has just the right velocity. At other points in the cycle, it has the wrong velocity. And so in order to figure out whether that just right velocity is the one that you predicted, you have to look and see, well, where did it happen in the cycle? So you have to actually look at the full data and look at the phase shift to see, all right, did it happen halfway through the cycle? Did it happen 40% of the way through the cycle? When in the cycle did it happen? But if that absorption event happens at just the right part of the cycle, when the thing is moving at just the right velocity, then indeed you can measure the Doppler shift from that. And you can say, all right, we needed to get absorption, we needed to get a Doppler shift of such and such, which would You can say, does that exactly cancel out the Doppler shift that Einstein predicted due to gravity? And it did. And that is how we knew that photons are shifted. So we've gone from talking about waves and oscillations to talking about electromagnetic waves to talking about Maxwell's prediction that electromagnetic waves travel at the same speed to all observers, but he didn't think too carefully about what that meant, to elucidating its consequences, to finding out that once we put gravity in, yes, they still go at the same speed, but they follow curved paths, and their frequency can depend on how far they have traveled in a gravitational field. To go any further with this, you should take a general relativity class. You should talk to Dr. Abdul Rahimi. She's the general relativity expert in our department. We are at the edge of everything I know about relativity, and that is as good a time as any to end. I will have a review session Monday afternoon. I will be available as needed for questions next week, and the final exam will be next Friday morning. The official time slot is 9 to 10:50. I'm going to start the exam a half hour before that and end it about a little more than a half hour after that, so that you have some leeway on both ends of it, depending on how your schedule works out. Any questions on anything? All right, well, good luck with finals, and I hope you have as good of a summer as you can have under the circumstances. And I look forward to seeing most or all of you in Math Methods this fall. Have a good day.